Welcome to UV Physics Academy. So here we are discussing quantum algorithms. In this eighth part, here we are discussing Grover's algorithm. Okay, so what is this Grover's algorithm? So here I divided this into 5 parts. Okay, first one, let me explain what is this algorithm, and I'm using some graphical representation to show that the order of the number of iterations is nearly equal to order of root n, capital N. Okay, so what is this algorithm? For example, we have some unsorted data which contains a capital N number of elements. Let us suppose this one. Okay, so in this data, we have our target somewhere and we would like to find that target. Okay, so our aim is to find x such that f of x equal to 1. So that is the target. This is the target. For example, if you are using any classical algorithm for this, in first attempt we may find that a target, or maybe last attempt we may find. So on an average, we can find this in order of n steps. Actually, n by 2 is the average. We can say the order of n steps. So if you are using a classical algorithm, so this is possible within order of order of n steps. But in this Grover's algorithm, we can achieve this within order of root n steps. We can find the target in order of root n steps. So this is what we are going to derive in this algorithm. Okay, so if you want to do this, first we have to create a superposition state. So let me create a superposition state. First one is a superposition state. How to create this? With the help of head maps. So here we have, let us suppose, okay, n number of qubits, okay, and head map gates, n number of head map gates are operating on this. This is just like a quantum parallelism, nothing but quantum parallelism. And here we got the superposition state. I am taking this as an initial state psi naught, which is equal to 1 over root n summation over x, and this is the ket x, where x is equal to 0 to n minus 1. Okay, so what does it mean? That means here we have the superposition. I'm taking the superposition of all these states. Okay, we can represent like this. Here we have all states. First one is a 0, sorry, next one 1, 2, 3, so on, and somewhere we have like this, and we can represent this as a 0, 1, 2, so on, and this is the last one is a n minus 1 state. All these are having a amplitude that is a 1 over root n. Okay, somewhere in the middle we have this a target state. Let us suppose somewhere in the middle we have this target state. Okay, so here I'm going to divide this into target state and a remaining state like this. That is 1 over root n summation. I am representing r for remaining states. So this is the remaining states and plus target state. So both the amplitudes are same for both the states. Amplitude is 1 over root n. Okay, I'm going to represent in another format, that is a psi naught. I am assuming for the calculation alpha naught, that means the initial amplitude. Okay, summation, this is the remaining state, where please remember that r definitely not equal to t for target. So plus a beta naught into t. Don't forget where alpha naught and beta naught equal to 1 over root n. Clear? So that's it. And here we have created the superposition state with the separating that remaining states and the target state. Initially, both are having same amplitude, that is 1 over root n. And let us see in this algorithm how we are, our final aim is to find this a target. That means the amplitude of target state should be increased, and whereas the amplitude of the remaining, all other remaining states will be decreased. Let us see how it is possible with the help of this Grover's algorithm. Okay. Right. So let us represent this graphically. So now I am assuming here we have, this is the remaining states, all the remaining states, and this is the target state. These are the remaining, R for remaining and T for a target state. Okay. So initially both the amplitudes are same, that is 1 over root n, alpha naught and beta naught. So that's why here you will be having this superposition state exactly in the middle. So this is the superposition state, and of course this is nothing but a psi naught. Okay, so here you know what is a psi naught? Alpha naught summation R for remaining, okay, and plus beta naught T for target, where R definitely not equal to T. Let us suppose it is making some angle theta naught, which indicates the slope. Okay, fine. Here in this case alpha naught and beta naught both amplitudes are same, that's why the line is passing through that origin. Okay, y is equal to mx, just like that. Okay, fine. And now in this Grover's algorithm we have two important operations. The first one is inversion about x-axis. So what will happen? Let us discuss what will happen. The first operation is about inversion of state, that is psi naught about x-axis. So for example, if you have this state psi naught, okay, and if you take the inversion about the x-axis, then it will become like this. The x coordinate will be as it is, but the y coordinate become negative. So the amplitude of y coordinate, the amplitude of that y axis, what is that y axis? There we have taken t. Okay, the amplitude of that target state will become negative. That's it. So with the help of this inversion about x-axis, what will happen? The target state, this will make inversion of amplitude of target state. Okay, so let me explain this graphically. If you take this like this, and here we have the initial state psi naught, and the angle is a theta naught, and this is psi naught or superposition state S. And if you take inversion about the x-axis, then this will be like this. So angle is the same, that is a theta naught, okay, but the only the thing is here the amplitude, earlier here we have beta naught, this is a plus, but this become minus beta naught. The target state amplitude become minus beta naught. So this operation is represented by IT, T for target, which is I minus 2 into the outer product target. Once you operate this IT on psi naught, the amplitude of that target state will become negative. That means this will become alpha a summation R is not equal to T, and this is R remaining minus, of course it is alpha naught, minus beta naught into target. So the first operation is done, and here we make that amplitude of the target state become negative. Okay, so keep it aside. And the next one is the most important, that is a diffusion operator. Diffusion operator. So what is this a diffusion operator? So here we have D equal to actually minus Hn I naught Hn. So what is this minus? Let me explain. In this diffusion operator, first we will operate the head mod operation, and after that we would like to change, or we would like to invert the amplitudes of all other states except 0. That means the 0 state amplitude, there is no phase change, but remaining all states amplitudes should have opposite a phase. If it is a plus, it should be minus, like that. Actually, our aim is to invert. Actually, we need to convert. Right. So we need to invert the amplitude of the states other than 0. But here you are using the operator I naught. So this I naught is nothing but I minus 2 the outer product 0. So this will invert the amplitude of a 0 state. So that's why to correct it algebraically, here we are using this negative sign. Okay, fine. That's it. And okay, but we are using I naught. I mean, instead of inverting the amplitudes of other state, we are inverting the amplitude of 0 state, and to correct that we are using a 1 minus extra in the formula. I hope you understand this. But in the circuit we won't show that. We will use this I naught only. And finally in the answer, once you make the measurement, you may get a extra phase factor of pi, something like that. No need to worry about that. And this is quite interesting. Let me explain what is happening here. For example, if you take this graph again, okay, so here we have, this is the initial state, and after inversion our state will become like this, and I can take this is the psi naught, okay, and I can take this is IT psi naught, this angle theta naught, and here also theta naught. Now once this diffusion operator, now we are talking about the diffusion operator. So once you operate this diffusion operator, so that which is nothing but a D. How to visualize physically what is the diffusion operator? It's just inversion about S, this initial state. So what is the meaning of inversion about that S state? So here this is the psi naught, okay. Now this is your S. Now I am taking inversion about S. Then finally here this will be the final state, sorry, this is the final state, and this final state will have an angle like this, and this definitely should be equal to theta naught, because you have taken inversion about S. I hope you understand. So here one theta naught and one more theta naught, so total 2 theta naught. So final state will make an angle 2 theta naught with respect to that superposition state or initial state. Fine. So if you observe carefully, this is our initial psi naught, okay. Now I make one time iteration, one time operation. What operation we have done? This one. This is a d I t operates on psi naught. Then your final state is making an angle 2 theta naught with respect to the initial state psi naught. Now let us suppose you operated r number of times, okay. So let us operate this for r number of times. Then what will happen? So your final state will be like this, or it comes close to this y-axis. So once again, so 1 time, 2 times, 3 times, 4 times, r times, like this. So this will be your final state. And now with respect to this initial, it makes some angle. Let us say this is a 2r theta naught. And if you observe carefully, as the number of iterations are increasing, the final state is coming close to the y-axis. Actually here, what is your y-axis? Target state. X-axis is what? The remaining states. So once it comes close to the y-axis, the amplitude of target state is increasing because the slope is increasing. Slope increases means what? Y coordinate is increasing, x coordinate is decreasing, then only slope will increase. So finally, ultimately, what is happening here? The amplitude of target states are target state is keep on increasing, and the remaining state amplitude is keep on decreasing. That's it. So graphically, we can visualize this, how the amplitude of target state is increasing and amplitude of remaining states are decreasing. So finally, after this diffusion operator, what's happening here? dit, okay, operates on psi naught. Okay, so we are getting this a final state, but in this final state, the amplitude of target state is keep on increasing, but whereas amplitude of remaining states so keep on decreases. Finally, some r number of iterations, it may coincide with the y-axis. That is what we are going to derive here, that number of iterations should be the order of root n. That is what we are going to derive, the number of iterations that should be the order of root n. Okay, so I hope you understand what is this Grover's algorithm. Okay, so let me explain the next part. Wait, so here again I have taken this a graph. Okay, so here what is happening one more time, here we have initial state. Let us suppose this is a psi naught, psi naught. Okay, and here one time I operate dit, then I got psi 1. Okay, so this is nothing but psi 1, that yellow color. And let us suppose we operated, that means we have done r number of iterations. Then what will happen? This is psi naught, okay, dit, r number of times operated, and finally we got psi final. Let us suppose this psi final coincides with the y-axis, then only the target state amplitude will become 1. Okay, so one more time, here what I am saying is, let us suppose r number of times operated. Okay, so then this will be your final state, and then it makes an angle. How much? Carefully observe, this is a 2r theta naught, not that middle one, from here to here. One more time, from here to here. So that is 2r theta naught. Okay, so now let us assume after some r number of iterations, it is coming close to the y-axis or coincide with the y-axis. Okay, then what will happen? For example, it coincides with the y-axis, let us suppose. Then if you take this total angle, so that means this angle, this will be 90 degrees. Then already up to this we have a 2r theta naught, 2r theta naught. I assume that it coincides with the y-axis. So then it will be 2r theta naught, and here one more theta naught. So the total is 2r theta naught plus theta naught should be equal to 90 degrees. And then we will get that r value. If you want to get this, first we need to find theta naught. So how to get theta naught? Just wait. Okay, so here I have psi naught equal to alpha naught summation r plus beta naught t, where r is not equal to t. This is the initial state. Now let us suppose dit, this is the Grover's iteration operator, dit, operated n times on psi naught. Then let us suppose we got psi n, which is equal to alpha n summation r plus beta n t for target here. R is not equal to t. Okay, so that means after n number of iterations, we got the amplitudes alpha n and beta n. Now apply normalization condition. If you take normalization condition, So which is nothing but here alpha n mod square, maybe it's a complex number, that's why we are taking mod square, and how many are there, n minus 1 plus beta n mod square should be equal to 1. So by using this trigonometric relations, we can show that this is alpha n square, simply I am taking alpha n square, n minus 1, this we can take it as a cos square theta naught, because along x-axis we have the remaining states, along y-axis we have the target state, and that beta n square should be sine square theta naught, because the adjacent side, okay, remaining states, and here we have opposite side, that is a target, okay. And from this we can find alpha n equal to, sorry, cos square theta, sorry, this is not a theta naught, I'm sorry, theta n, because here n number of iterations are there, I'm sorry. So from this I can find cos theta n is equal to n minus 1 under root alpha n, and from this sine theta n equal to beta n. So from this I can write what is cos theta naught. Cos theta naught equal to alpha naught into under root n minus 1, and sine theta naught equal to this beta naught, which is equal to 1 over root n. Okay, and here also this can be written as cos theta naught equal to under root n minus 1 by root n. Okay, so that's it. Finally we got this relation, right? So just keep it aside. Now let us go to let us do some school algebra. So just now I told you, whenever as the number of iterations are increasing, and then the final state will come close to the y-axis, come close to the y-axis. Okay, so now let us suppose it coincides with the y-axis. Let after r number of iterations, okay, so psi final coincides with y-axis. Okay, right. So once it coincides with y-axis, I hope you understand what I am discussing here. Then this angle should be 90 degrees. So that implies 2r theta naught plus theta naught should be equal to 90 degrees, pi by 2. Okay, so from this we can find, we can take out common theta naught. So that's why 2r plus 1 equal to pi by 2 theta naught. You can bring this theta naught this side, and our aim is to find r, so that's why r is nothing but pi by 4 theta naught minus 1 by 2. We'll bring 1 this side, and after that divide with 2. Okay, so now let us suppose we have a very large number of elements. Then what will happen, that a capital N is very large, then it is in the denominator, then sine theta naught is 1 over root n, so this is very small. Whenever theta is very, sine theta is very small, okay, so then we can say sine theta naught is nearly equal to theta naught. For example, if you see sine 0, 0, sine 0, 0. So if theta is very small, we can take sine theta is nearly equal to theta. So with the help of this, and we can replace this theta naught with 1 over root n. So this is nothing but pi by 4, and root n will go to the numerator and minus 1 by 2. And we got the number of iterations r is of order of root n. Okay, so that's it. So I hope you understand this algebra it's not at all difficult. It's a very simple school level algebra here we have used, and let me explain briefly one more time. Here we have some unsorted data which contains a capital N number of elements. Our aim is to find the target. Okay, first we have created a superposition state with all states including target state. After that, just we separated a target and remaining states. Okay, and of course the amplitudes are same, and this is the graphical representation. So this is graphical representation of the initial state. Why it is passing through the origin means both the amplitudes are same, remaining and the target state amplitudes are same initially. And the first operation is this one, that is the inversion about x-axis. Once you take the inversion about x-axis, if you take that, then you will get the y coordinate as a negative. So that's why beta naught become minus beta naught. That is amplitude of target state is inverted. And after that, this is the most important, and the next one is the diffusion operator. So mathematically that is a minus hn I naught hn. Okay, but here the point is we would like to invert the amplitudes of other states, not zero state. But here we are using I naught operation as I naught as the oracle, which invert the amplitude of zero state. So for that, in the algebra, to correct that, here we are using a minus sign extra. And the next beauty of this algorithm is, this is your initial state, and you are inverting the amplitude of target state, and from here you are applying the diffusion operator, that is the inversion about s. Already it is making some 2 theta naught with respect to s. Okay, then once you take the inversion about s, this will be the final state. Like this, if you are doing some number of iterations, finally it may come close to the y-axis. So what is the meaning of coming close to the y-axis? The amplitude of the target state is increasing and the amplitude of remaining states will decreasing simultaneously. Okay, so that's it. And here I just used the trigonometry school level algebra to show that the order of, the number of iterations equal to order of root n. So thank you, and we will explain in the next part about the algebra. So we will find the iteration matrix, operator form iteration matrix we'll find in the next lecture. Okay, so thank you.